Welcome to the One World Cow seminar. Our speaker today is Sebastián Barbieri, who is currently in Santiago, Chile. He's going to speak to us today about indistinguishable and multidimensional Sturmian configurations.
Great, thank you very much. So I have to say, this is joint work with Sebastián Barbieri from Bordeaux and Stepan Starosta from Prague. All right, you've all seen the cow. Let's go ahead. So I'm going to begin with a few definitions. Sorry about this. These are very simple definitions. If I'm not being clear about anything that I'm saying, just please don't hesitate to stop me and ask questions. Otherwise, online talks get very, very boring. So for the rest of the talk, A is going to be a finite set, which I'm going to call an alphabet, and D is going to be a positive integer. I'm going to say that a configuration is going to be a map from CD to A, so it's going to be things like this. For instance, if I take D equals 2, and I take A being 0, 1, 2, my finite alphabet, then a configuration is just a map from set squared to 0, 1, 2, like the thing you see there, okay? So a configuration on the plane. All right. Okay, so those are the objects I'm going to be considering during this talk. I'm going to say that two configurations, as the one you saw before, are asymptotic if they differ just in some finite subset of set to the D. So, for instance, if I take two configurations X and Y as the ones you see here, I have X, I have Y, they are going to be asymptotic if they just differ in finitely many positions. So for instance, these two differ in these three symbols that I'm showing over here. Can you see my pointer?
Yes, yes, we can.
Great, great, great. So, okay, I drew them so that they differ exactly in those three positions. You have to imagine these are infinite configurations and they coincide everywhere else. They're just differing in these three symbols. And given two asymptotic configurations, I'm going to call the set of positions in Z to the D where they differ, their different set. All right. So I have configurations. I have defined what it means to be asymptotic, and I have defined their different set. Now, I want to answer some question that might have come to you. Why am I calling these things asymptotic? There's a reason why they are called asymptotic. It comes from dynamics. I'm not really word combinatorics type of guy. I'm more an ergodic theory and group theory guy. So I feel the need to answer why am I calling this notion asymptotic. If I take the ZD action on the set of all configurations, which just translates configurations by a fixed vector. So I take sigma, the ZD action on A to the Z to the D, where I just grab a configuration and I shift it by a fixed vector on Z to the D. Then two configurations are going to be asymptotic if and only if for any sequence of integers whose norm goes to infinity, then the distance between the configurations goes to 0, where the distance is just, well, any distance which generates the product discrete topology on the space. All right, so just a simple example. Two configurations are going to be similar if are going to be very close if they coincide on big intervals. So for instance, if I have these two asymptotic configurations X and Y, X is just all zeros on Z, Y is all zeros except for one position where I see a 1, and I start shifting. So here I have X and Y, and I start translating. So I take sigma, the symbols move to the left, sigma squared, sigma to the 3, 4, 5, 6, 7, 8, 9, blah, blah, blah. Eventually, if I fix any finite interval, they're going to be the same. So that's why the name, where the name asymptotic comes from. And this notion that I gave that two configurations differ on just some finite set is equivalent to this definition I'm giving before. Okay, so it's really a notion that comes from dynamics. All right, so I'm going to consider two asymptotic configurations. And given a finite subset of Z to the D and a pattern that's just a coloring of this finite portion of Z to the D by symbols in A, I'm going to consider the cylinder given by this pattern as the set of all configurations such that restricted to this support S gives me P. And what I want to do in this talk is I wish to compute in some manner, in some way, how many times a pattern occurs in some configuration versus how many times it occurs in another configuration. So essentially, I want to do something like this. I have two configurations, X and Y, and I want to sum over all positions, whether I see P at that position in X minus whether I see P at that position in Y, or vice versa, Y and X. Okay, so as I define this here, it's kind of weird. It's not well defined. I'm summing over infinitely many positions, but it turns out that if X and Y are asymptotic and they differ in a finite set F, then this sum is actually finite. I'm just summing over finitely many positions because outside from some finite set, they are exactly the same. So if I try to see whether some pattern occurs, either it will occur on both of them or on none of them. So I'm going to get infinitely many zeros in this sum and finitely many non-zero terms. So if I have an asymptotic pair of configurations, this delta P makes sense. It's just a finite sum. All right, so this is just some measure of given some pattern, how much these two configurations differ. Well, maybe I'm seeing one pattern 3 times in one configuration and 2 times in the other, and then I'm gonna get a difference of 1 or -1. And I want to consider a very special kind of asymptotic pairs. I'm gonna say that an asymptotic pair is indistinguishable if for every single pattern P, I see it exactly the same number of times in X as in Y. So of course, this might appear infinitely many times, but if I look at the part where they are different, and I look at only the portion where they intersect the difference set, this is a finite number, and I'm gonna say that the asymptotic pair is indistinguishable if this number is 0 for every pattern P. So that means that the pattern occurs exactly the same number of times in X as in Y. Okay, it's a very, very restricted notion. Okay, so here's an example. I'm gonna take this asymptotic configuration that I showed you before. Of course, this notion is not finitely checkable. I would need to check infinitely many supports to say that they're indistinguishable. But let me show you that these two configurations, X and Y, have a delta P is equal to 0 for all P with support S, that set that I'm giving you above. So let me zoom on them. Here is just the restriction to a small rectangle near the origin. And I'm gonna look at all patterns with support S, which I've marked here on blue. So for instance, if I look at this inverted L or something that I'm putting here, I see the pattern 0, 2, 1, 1 that appears on X, and I can count how many times it appears in X and in Y. And I can check that it occurs exactly once in X and in Y, in these two different positions. Then I can check this one, 2, 1, 1, 0. Well, it appears exactly once there. This one, 2, 1, 0, 2, it appears exactly once, and so forth. I check all the positions where my support intersects the difference set, and I check that, oh, okay, actually I have a one-to-one correspondence. So for all patterns with this support, I'm gonna get this delta P xy equals to 0. All right. So my notion of indistinguishability is that this happens for every single finite support. All right. Are there any questions so far? All right. So this is the notion that I'm going to be considering during this whole talk. I'm going to take asymptotic pairs. I'm going to consider an indistinguishable asymptotic pair. And I'm going to try to figure out what this can be, right? Maybe it's something, there are only trivial asymptotic pairs described. I'm going to try to figure out what they are. But so let me just tell you some very, very simple examples, trivial examples. If I take the trivial asymptotic pair where the difference set is empty, so XX for any configuration, well, this is by definition an indistinguishable asymptotic pair. It's extremely boring, right? I see exactly the same in both of them. So of course it's indistinguishable, and I'm gonna call these trivial pairs. Okay, not very interesting, but okay, so it's life. There's another one which is a little bit more interesting, still very simple. if it turns out that two configurations are asymptotic and they are on the same orbit of the translation action, so that means that sigma n is equals to y for some n in ZD, then they are automatically indistinguishable, right? Here you see an example below. I have this configuration X, which has a heart of ones and zeros everywhere else, and I translate it so that my heart is here. I've marked the different set on red, or with a slightly different color. And they're going to be indistinguishable because, well, every pattern is going to occur exactly the same amount of times in X as in Y, so the sum is going to give me 0 anyways. So those are two very simple examples that one might get to show that this definition is not entirely trivial. And a few years ago, I think it was during 2019, I started looking at the question whether, well, are there any indistinguishable asymptotic pairs which are not on the same orbit? And I was just asking this question for configurations in Z. Can I find an indistinguishable asymptotic pair where both configurations are not on the same orbit? And well, it's a little bit hard to get the right answer. Before going any further, though, I want to tell you about my motivation. Why am I considering this definition of indistinguishable asymptotic pairs? Because, of course, in mathematics, sometimes one just says, okay, I'm going to consider some definition and go ahead and try to figure out what it gives me. But no, here there's actually some reason why I'm looking at these pairs, and it comes actually from thermodynamical formalism. So just bear with me for the next 3 slides. I'm going to try to tell you what my motivation was to study these objects, and then we're going to go back to combinatorics on words. So let me just give you the premise of thermodynamical formalism in a nutshell. Forget about everything I said before, and consider n little balls, 1, 2, 3, up to n, with some real weights given by a map. What is the probability distribution on these n balls, which maximizes the entropy of the probability distribution plus the average weight with respect to that measure? So essentially, I want to find the measure which maximizes the entropy plus the integral of f. And that's exactly, well, I'm maximizing mu over the entropy, which is summing minus mu I log mu I. And then I'm summing the integral of f, which is just f of I times mu I. Okay, that's there's some reason why that comes from physics why this might be interesting. And the answer is the famous Boltzmann or whatever. It's not a hard problem. You can show that exactly these distribution. Okay, so can distribution to sets of configurations, and this gives you a notion which is called Gibbs measures. In a nutshell, this is what Gibbs measures are. You take configurations, say on Z square, and a measure is going to be Gibbs if it follows Boltzmann, and the blue part is changing. So I can have different patterns inside this blue thing. For instance, I might have this pattern for some configuration. I might have this other pattern. And a measure is going to be Gibbsian if the conditional measure, if the conditional expectation of the event of seeing one pattern on whatever's outside and the measure of seeing the alpaca looking to the left condition whatever's outside follows Boltzmann distribution from some f. That means if I fix everything outside some finite window and I look at the finitely many configurations that appear inside, then this probability distribution condition on the outside must follow Boltzmann's distribution. And that's the notion of Gibbs measures in a nutshell. All right, so what does this have to do with indistinguishable asymptotic pairs? Well, I can denote the set of all asymptotic pairs by xy by a, so that's some relation. The Boltzmann distribution of a Gibbs measure, I can determine it by some cocycle on the asymptotic pairs. So I can just codify this Boltzmann distribution by something called a cocycle. That's a map from the asymptotic relation to the reals, which satisfies the usual cocycle relation. as a boundary relation on a graph. And well, for instance, some very trivial thing, if all configurations are equally likely, I mean, the weight function is 0, then I get the cocycle 0, which is the most boring one. And the sole Gibbs measure is the uniform Bernoulli measure on the set of configurations. Okay, so again, what does this have to do with indistinguishable asymptotic pairs? Here it comes. If I look at the space of continuous shift invariant cocycles, it turns out that this thing is a Banach space with some appropriate norm. So, okay, I can take this space of cocycles and I can linearize it and I can make it a Banach space with some nice norm. And in this Banach space, there's a natural evaluation map. If I just have some asymptotic pair, I can evaluate my cocycle in the asymptotic pair and I get a continuous map to the real numbers. And the nice thing is that the strong norm on this dual space depends on these delta P things that I gave you before. So I need to count the difference of how many times a pattern appears in X and in Y to figure out the norm of these evaluation operators in the dual space. So the real reason I'm looking at indistinguishable asymptotic pairs is because indistinguishable asymptotic pairs characterize the asymptotic pairs, which give me the trivial evaluation functional. So in some way, they are the kernel of this map, even though asymptotic pairs are not a vector space, but they describe the ones that give me the 0 map. So if I understand them, I understand all the elements in this dual space and I can do functional analysis magic. Okay, so that's my motivation for looking at indistinguishable asymptotic pairs. It's connected to Gibbs theory in some not so obscure way. Okay, all right, so that's motivation. From now on, you can forget completely about Gibbs measures and everything I said. Let's go back to combinatorics. So back to the question. Are there indistinguishable asymptotic pairs which are not on the same orbit? And I'm just going to restrict my question for Z, for the integers. Well, I was looking at this question after doing this Gibbs theory stuff, and I asked Tom Majerovich it was 2018, and he said, probably not. It should be possible to prove that there are no non-trivial asymptotic pairs using the fine and wheel theorem. I tried for some time. I failed. I didn't manage to prove this, so I gave up. And next year, I was in Bordeaux with Sebastián Barbieri, and I asked him the same question. And he said, probably not. It should be possible to prove this using the fine and wheel theorem. Once again, we tried for some time, and we failed. And then, later on that year, I was in Prague, and we asked Stefan Starosta, and he said, probably not. It should be possible to prove this using the fine and wheel theorem. And then I said, okay, enough with the fine and wheel theorem. This doesn't work. And we started working, trying to find, is there maybe another way to prove that there are no more indistinguishable asymptotic pairs? And we actually ended up characterizing all of them. So the theorem is that, yes, there are asymptotic pairs which are not on the same orbit. Moreover, we completely characterize them on Z. We have a full characterization of asymptotic configurations that give me indistinguishable asymptotic pairs. And the interesting thing is that they are closely connected to Sturmian codings of irrational rotations. In fact, we discovered a new characterization of Sturmian configurations through these indistinguishable asymptotic pairs. So we were pretty happy about that. All right, so let me tell you about this proof on Z because it's not that complicated, and I think I can give you the main idea of how this goes. And then I'm going to move to higher dimensions where things start getting a little bit more complicated, but at the same time, more interesting. So let me remind you of the definition. An asymptotic pair is going to be indistinguishable if and only if for every single support and pattern with that support, I see this pattern exactly the same number of times in X and in Y, where number of times means intersecting the different set. So just some very simple thing. If I take a sequence of supports, finite supports on Z to the D, that grows up to Z to the D, then XY is going to be indistinguishable if and only if this condition happens only on patterns with support some Sn. That means I don't need to really test all finite subsets of Z to the D. It suffices to check, say, rectangles or words. I don't need to look at, say, words with gaps in the middle. I can just look at convex supports, for instance. Second thing, if I have an indistinguishable asymptotic pair and I apply some affine transformation, that means some translation or some automorphism of my group, then it's still an indistinguishable asymptotic pair. That's just very easy to check. So these things are invariant under the shift map, and they are also invariant under automorphisms, like, say, exchanging the negative numbers with the positive numbers, something like that instead. Another thing, if I have an indistinguishable asymptotic pair and I have a sliding block code, so that's just a function from the set of all configurations in some alphabet to the set of configurations in another alphabet that depends on finitely many symbols to determine a particular symbol, and which is invariant under translations, then, well, the image of X and Y is also going to be an indistinguishable asymptotic pair. So this property is preserved by applying sliding block codes. Moreover, it's stable under limits if I take my limits in a very precise manner. I'm going to say that a sequence of asymptotic pairs converges in the asymptotic relation to an asymptotic pair XY. Well, if both sequence of configurations converge to X and Y, and also if the different set is contained in some finite subset of Z to the D for every for large enough M. So this is some notion of convergence slightly stronger than just convergence on each coordinate. And with this notion, limits of indistinguishable asymptotic pairs are also going to be indistinguishable asymptotic pairs. So this notion is kind of stable under most of the things that one would do on symbolic dynamics. All right, let me just show one of these things for a change. I'm going to show another property which starts giving me some structure. Remember that I said, well, trivial pairs, XX, are indistinguishable, and also indistinguishable asymptotic pairs which are on some orbit. And what one can show is that there's actually a great divide. If I take a non-trivial indistinguishable asymptotic pair, and one of these two configurations is non-recurrent, then they necessarily lie on the same orbit. That means that if I am going to get some non-trivial example, they are going to be recurrent. So the proof is quite easy, so I'm going to do it. Suppose one of these configurations is non-recurrent, then I can find some pattern that occurs exactly once, right? There is some pattern with some support that occurs exactly once in my configuration. Well, this my pair is indistinguishable. So if it occurs exactly once in X, it must occur exactly once on Y, on some other position. Okay, so I have this pattern that occurs in X and in Y. And what I can do is I can start looking at bigger and bigger supports which contain the support of P. So I'm going to take a sequence of supports that grow to Z to the D and which contain the support of P. And I'm going to take a bigger pattern, which is, well, the restriction of sigma kx restricted to this big support. Well, this support contains P, so it must occur exactly once in Y. So this thing, X belongs in Pn, so this n is unique, so this thing must also happen in Y. And well, the intersection of all these patterns as Sn goes to infinity is just going to be the singleton with sigma k of X, so I'm just going to see the shift of X. So the only thing that I could have is that sigma k of X is sigma m of Y. So these two configurations need to coincide up to some shift. So that shows that if I have an example where my configurations are not recurrent, then necessarily it's a trivial example. They need to be on the same orbit. Okay, so we can assume now that we're going to have recurrent things. And for the rest of this part of the talk, I'm going to restrict to Z because life is easier. The proofs are much nicer and I have stronger properties. The first one is if I have a non-trivial indistinguishable asymptotic pair and the pattern turns out to occur in X, then necessarily it must occur intersecting their difference set. And this is something very strong because it will give me a bound on its complexity. And the proof is simple. Imagine I have this indistinguishable asymptotic pair X and Y, and I see some pattern that occurs in X, like these last four symbols, 1, 0, 0, 1. I want to show that it occurs in Y. So what I'm gonna do is I'm gonna take the first occurrence of this pattern to the right of the difference set. If it exists, to the right. If not, I take the first to the left. Okay, suppose it does not intersect the difference set, and take the first that appears on the right. Now take this pattern and extend it just that so that it touches the difference set on just one symbol. Well, this is a pattern which is intersecting the difference set. It occurs in X, so it must occur in Y. And it can't occur in Y in the same position because the last symbol is switched. So necessarily it must occur earlier. Either it intersects the difference set and I'm done, or I just move this realization of this pattern to the left in the part where they are asymptotic. So I'm going to have another occurrence to the left of the original one that I picked, and I picked it as the closest one, so I get a contradiction. So I get that every pattern must intersect the difference set, and this immediately gives me a complexity bound, right? If all patterns of length n that occur in these configurations intersect the difference set, well, then that means that I have at most k plus n minus 1, where k is the length of the difference set if I look at it as an interval, right? So this gives me a very strong complexity restriction. Of course, what you're thinking now is take f equals 2, which is the smallest one, and then you get that the complexity is bounded by n plus 1. So it's starting to resemble a lot Sturmian configurations. And well, here's the next part of the proof. I can prove this happens exactly on Z, just on Z. It's not true on Z to the D. If I have a non-trivial indistinguishable asymptotic pair, which is recurrent, then I can show that in fact it's uniformly recurrent. The proof is just playing with things, with words, as I did on the last proof. And the interesting thing is, well, if I take an indistinguishable asymptotic pair with X recurrent and difference set, two symbols, 0, 1, then they are uniformly recurrent, and the complexity is n plus 1. It cannot be n for some symbol because otherwise I would get a periodic configuration, and that's not going to work. So they must be Sturmian configurations. Okay, so somehow I got that if these things do exist, then they are Sturmian configurations. Okay, so just, I know this is a Combinatorics on Words seminar, so I should validate what Sturmian codings are, but let me do so anyways. If I take some irrational in 0, 1, and I take the rotation on the circle given by, well, adding alpha modulo 1, and I take this partition where I take, well, 0 up to 1 minus alpha and 1 minus alpha 1, this one. And I just look at the orbitals of some point, say I start in 0, and well, I got into P1, so I write a 1, move to 0, I write a 0, and so forth. Well, this is an invertible map, so it gives me a function from Z to 0, 1, and this thing is what I'm gonna be calling a Sturmian configuration. I choose some starting point, I start moving by the rotation, and I just encode what I see. In which interval do I fall? And according to that, I get a sequence, an infinite sequence of symbols. So formally, this means take an irrational and let C alpha be the configuration given by, well, this can be coded exactly by the floor of alpha times n plus 1 minus floor of alpha times n. You all know this. And if I change the partition, well, the only thing that changes is that floor is changed by ceiling. I just, in the previous partition, I took intervals which are closed on the left, open on the right. Now they are open on the left, closed on the right. I did just a small change. And the thing is that if I look at these two things, they are only going to differ in positions 0 and minus 1. And thus they are just going to be, they are going to be an asymptotic pair with difference set size 2. And what I can prove is that these characteristic Sturmian configurations, C alpha and C alpha prime, are going to give me an indistinguishable asymptotic pair. In fact, I don't just have this property that the sum of all patterns intersecting the different set is 0. In fact, every pattern in the language occurs exactly once intersecting each of their different sets. So every pattern occurs exactly once, and that's because of the fact that the complexity is going to be n+1. Okay, so this is nice. We get this small theorem. If I have x and y is 0, 1 to the set, and I assume that x is recurrent, then the following are going to be equivalent. xy is going to be an indistinguishable asymptotic pair with different set -1, 0, such that x minus 1, x0 is 1, 0, and y minus 1, y0 is 0, 1. And there exists an irrational alpha such that x and y are precisely the lower and upper characteristic Sturmian sequences of slope alpha. So this indistinguishability notion characterizes Sturmian configurations. But actually we get a little bit more. In fact, if I look at the non-recurrent case again, I can always obtain it as a limit case of Sturmians. So I get this slightly stronger theorem. If I just have a pair of indistinguishable configurations, then they are going to be an indistinguishable asymptotic pair with different set -1 and 0. If and only if there exists a sequence of irrationals which converges to some rational number such that x and y are going to be the limits of these two Sturmian configurations. So, okay, I can get the non-recurrent case from the recurrent case. And in fact, I get even more. I get a full characterization. This is just for indistinguishable asymptotic pairs with different set Q. Q positions differ, but the general case can be obtained through substitutions. So this is the real theorem on Z. If I have a finite alphabet and I have a non-trivial asymptotic pairs, that's x is different than y, then xy is indistinguishable if and only if either x is recurrent, in which case there exists an irrational and a substitution and an integer such that x and y are just going to be, well, I take my Sturmian configuration C alpha and C alpha prime, I shift them once so that the different set now becomes, it's all on the negatives, -1, -2. I apply my substitution, and then I shift it up to some integer. And that characterizes all recurrent indistinguishable asymptotic pairs. If x is not recurrent, then I can actually, there exists some substitution and an integer such that I can do exactly the same, but I just need to start from this configuration where I have all zeros, 1, 1, all zeros, and one shift of this configuration. So I can obtain absolutely everything from these two configurations, everything which is not recurrent from these two configurations. Okay, so we were very happy. We found a full characterization on Z, but we were, especially for Gibbs theory, we were very interested in the multidimensional case. So on the remainder of this talk, I want to talk about what happens if the dimension is bigger than 1. And things start getting more complicated, right? As a lemma before, I showed that every pattern which occurs in some indistinguishable asymptotic pair must intersect a different set. That's false for the multidimensional case. Second thing, in Z, recurrence implied uniform recurrence. That's false for d bigger or equal than 2. And the worst part is that substitutions do not help us reduce the problem to a smaller size different set, which is what happened in the previous case. So here we cannot really use substitutions. Things get more geometric. That's because there's no reasonably nice notion of the right sequences that works in this setting. And in general, these things have no complexity bound in many dimensions. They could have a very small difference set, and the complexity of the cardinality of the alphabet even can be as high as you want. So here's an example just to break down illusions of these things being nice. Here in the middle, on the central horizontal line, I put the Fibonacci sequence, the two characteristic configurations of the Fibonacci sequence. These are indistinguishable asymptotic configurations on Z. And now I'm extending everything else by just a third symbol, Q. It's not hard to check by hand that this gives me an indistinguishable asymptotic pair. But now, look, it's not, it's recurrent, but it's not uniformly recurrent. The ones say they don't appear far if I start moving vertically, they don't appear again. So it's not gonna be uniformly recurrent. Also, some patterns do not occur in the difference set. The 2 does not occur. And I could do the same here. Instead of putting 2's everywhere, I can start putting, say, other rows of symbols, all 3s, all 4s, all 7s. I don't care. It's still gonna be a uniform, an indistinguishable asymptotic pair, and then the complexity can be as high as I want. So, okay, these things are more complicated. That means I'm gonna need more assumptions to get something interesting. So let me first tell you what the theorem is gonna be, and then I'm gonna define the terms. I'm gonna get D bigger or equal than 1. I'm gonna take an asymptotic pair with D plus 1 symbols, so the dimension of the space plus 1. And my difference set is gonna be, before I took 0 and minus 1, now I'm gonna take 0 and minus all the canonical vectors of Z to the D. So say in Z square, I'm gonna take 0, the position to the left and the position below. And here I have, this is gonna be the characterization I'm gonna show. I'm gonna show that indistinguishability plus some technical condition, which I'm gonna call the flip condition, and uniform recurrence is equivalent to being a multidimensional Sturmian configuration for some totally irrational slope of. Okay, now I'm gonna define this, what all of this means. And before that, I'm just gonna tell you the theorem is stronger. In fact, if I have just an asymptotic pair, which is uniformly recurrent, and which satisfies this technical condition, flip condition, then I'm gonna be able to show an equivalence of many different things. The pair is gonna be indistinguishable if and only if for every non-empty finite connected subset and pattern which appears either on X or in Y, then P will intersect the difference set exactly once in both X and Y. So this is stronger than being indistinguishable. Third, I'm gonna get what the complexity of the configurations is. So for every non-empty finite connected subset of Z to the D, I'm gonna have that the complexity with support S of X and of Y is gonna be exactly the size of the difference set minus the support, where this minus is the minus sign on Z to the D, it's not the difference of the sets. I'm just taking all positions in F and I'm subtracting all positions in S as integers in Z to the D. And I look at that set, I take its cardinality, and that's gonna give me the complexity for every finite connected support. And fourth, well, they are gonna be characteristic multidimensional Sturmian configurations from some totally irrational slope alpha. So the theorem gives me a complete description of the complexity of multidimensional Sturmian configurations for any dimension and any finite connected support. So let me tell you what multidimensional Sturmian configurations are, because I haven't defined them. It's very simple. Instead of taking one rotation on the circle, I'm gonna take D independent rotations, and I'm gonna take the obvious partition and do exactly the same. So I take D numbers on R to the D, I take the rotations, and I'm gonna suppose that this vector, 1, alpha 1 up to alpha D, is independent over the rationals, so I don't get periodicity. This is what I'm gonna call a totally irrational vector. Then the ZD action on the circle generated by this thing is free. I have no periods. Then if I take the partition of the circle generated by refining the Sturmian partitions for every single I can, well, do the same with now intervals closed on the right and open on the left. And the characteristic Sturmian configurations of slope alpha are going to be the codings of starting on the vector of all zeros and apply this action of Z to the D, look at the whole orbit, and in every position just mark exactly in which partition I'm in. So it's this, right? I have my vector alpha 1 up to alpha D in 0, 1 to the D. I order it using some permutation so that the largest number comes first and the smallest number comes last. And then the partitions are just going to be this one. So I start in 0, I go to 1 minus alpha T1, I go from this one to 1 minus alpha t2. And in the first one, the one that's on the top, I take intervals which are closed on the left, open on the right, and below I do the opposite. So this can be, of course, expressed just with formulas. If I take this vector alpha 1 up to alpha d, C alpha is just going to be what's written there. C prime alpha is just going to be what's written there. So essentially, it's just, I grab the usual one-dimensional Sturmian configurations and I add it on every dimension. I just out all of them. Okay. So it's not hard to see that in this case, this pair of configurations are going to be asymptotic, and the difference set is going to be just, well, the origin and minus all the canonical vectors. So the picture from the beginning that I showed you, this x and this y, which are different here on 0, 1, 2 and 2, 0, 1, they are actually they are going to be a multidimensional Sturmian configuration, C alpha and C prime alpha. For alpha, the vector square root of 2 over 2 and square root of 19 minus 4. These numbers we're choosing just for fun. No particular reason, just irrationals that lie in 0, 1. So, okay, for every totally irrational vector, I can construct these things. These are multidimensional Sturmian configurations. And let me tell you what this flip condition is. I'm going to say that an asymptotic pair satisfies the flip condition if, first, the difference set is the same difference set that the Sturmian configurations have, so 0 and minus the canonical vectors. Second, the restriction to the difference set is a bijection on the alphabet. That means every symbol occurs, and also I see a 0 on x0. And second, if I look at the position yn, then it is equal to xn minus 1 modulo the number of symbols that I have for every thing. That means, essentially, that these indistinguishable asymptotic pairs induce a permutation of the alphabet when I look at all the positions. So if you look at here, on the left I have 0, 1, 2, right? If I look at where the 0 is on x and where the 0 is on y, well, then I can look where the 0 is on y. Here I see a 1, so 0 goes to 1. 1 appears on the bottom on y. Here I see a 2, so 1 goes to 2. Then I see where the 2 appears on y. It appears on the origin, 2, and then 2 goes to 0. The flip condition is just telling me that this induces a permutation of the alphabet, if I just do that procedure. Now, where does that come from? It comes from geometry. You all know that these multidimensional Sturmian configurations, they are really coming from cut and project schemes. So what I'm really looking at here is just a discrete plane in the case of d equals 2. And what I'm going to see is that the cube at the origin gets flipped. And this flip condition is just combinatorially encoding all that information, that I'm flipping the hypercube at the origin. Okay, so there's some geometric interpretation behind this thing. And what we can show, I'm putting back the theorem, is that if I have an asymptotic pair, x and y, which is uniformly recurrent and satisfies the flip condition, then I have all these characterizations. The asymptotic pair is indistinguishable. Each pattern intersects exactly once the difference set. I know exactly what the complexity is. And these things must necessarily be the characteristic multidimensional Sturmian configurations of lobe alpha. I'm not putting the whole proof here because the proof is considerably harder than dimension 1. There's a lot of technical lemmas and things I don't want to bore you with. But let me just focus on the third part of the characterization. Now I have, if I look at indistinguishable asymptotic pairs, I have a complexity characterization of multidimensional Sturmian configurations. What's that? Well, the language we support any finite connected subset has the size of the difference set minus s. So here's an example. Suppose I take a Sturmian configuration C alpha on 2 dimensions, so a multidimensional Sturmian configuration with dimension 2. And for some reason that I don't want to know about, you want to know how many patterns with support S there are, where S is this 4-like figure. You just want to know how many you have. for some mysterious reason that I don't want to delve into. So for D equals 2, the difference set looks like this, the origin and minus the canonical vectors. So I just need to compute what is F minus S. So if I take F and I subtract the vectors in S, I get that, and that. Okay, I just inverted S and I overlapped it with F. So that's F minus S. So what's the answer? Well, I just count the number of squares. If I'm not wrong, that gives me 14. So yeah, 14. So there are exactly 14 patterns which support S on any two-dimensional Sturmian configuration. It's a handy formula and it's pretty. Okay, let's look at some support which is more interesting. Suppose I take D integers and I have a rectangle, right? Usually when you look at complexity of multidimensional configurations, you look at rectangles because they are more interesting. So suppose I take R, well, just the rectangle where the sides have length mi. And the formula here is pretty beautiful. I can show that the rectangular complexity of a multidimensional Sturmian configuration is just, well, I take the product of all the lengths and I multiply that by 1 plus 1 over the first length plus 1 over the last length. How do you compute this? It's really easy. You have the difference set, which is the origin minus the canonical vectors. So if you take the rectangle, well, you get that. And each time you move by one canonical vector, you have to add one of the D minus 1 dimensional faces. So that's why you get a 1, the size of the rectangle, plus the size of all the D minus 1 dimensional faces. So the interpretation is rather obvious. But it's pretty because it generalizes this usual Sturmian formula, right? For D equals 1, you recover that the number of words of length n is exactly n plus 1. And this is how it generalizes on D dimensions. Okay, so that's everything I wanted to talk to you about. Thank you very much for your attention. And here are the articles if you want to look at them at some point.
Oh, thank you so much, Sebastián. Does anyone have any questions? So is there any connection between this stuff and Nivard's conjecture stuff?
There is some, not directly. I mean, this is not going to help you solve Nivard, but this is something that Sebastián Lavey is more comfortable with. But there's the dual question, right? You could ask about Nivard, okay, suppose you have very low complexity, when do you become periodic? You could also ask, which is the lowest complexity that you can have and still be free, right? As an action of set, right? Have no periods at all. And of course, there are very simple examples where this does not happen and they have low complexity. But if you start asking the question in terms of minimal subshifts and stuff like that, it starts getting more interesting. So what we can do here is we can give a lower bound for the dual Nivard conjecture if you want.
Mm-hmm.
Right, so we know how to construct these multidimensional Sturmian configurations and we know how to compute the complexity for every finite connected support. So, okay, you can think of this as some lower bound. It's not really close to a proof or anything, but it just gives some info on that problem. So, not really strong. It's not very connected, but okay, that's the best I could do.
Right. Okay, we have a few questions in the chat. The first question is from Benjamin Helluin. Is the cow in the first slide an alpaca in disguise?
Well, you'd have to ask her. I don't know. I just got it from Google. I didn't have time to ask many questions. I just stole the picture and put it there. You're gonna have. I can send you the link of the. It's actually a tutorial on how to draw a cow. It's a video, and I can send you the link, and you could try asking the cow yourself.
We also have a question from Dan Rust. Would indistinguishable proximal pairs be something worth looking at?
Maybe. Yeah, I think it might be interesting. I don't think you would get a very nice interpretation in terms of Gibbs theory, as in this case. Well, maybe you would, because yeah, but okay, but you wouldn't have. You would have to look at something different than the asymptotic relation. Yeah, it might be interesting. I haven't thought about it. It might be interesting.
All right. Another question from Dan says thanks. There's a question from Pierre Bayard. Does your argumentation on Z work also on N?
Well, not directly. No, not directly. You have a problem defining indistinguishable asymptotic Sturmian indistinguishable asymptotic person, and you don't get exactly the same characterization. You need to look at the left to get exactly one occurrence of each pattern in the different set. In N, you don't. If you get asymptotic Sturmian configurations, but they are not indistinguishable with this definition. So you don't get exactly the same. You need to look at set to make this work.
Okay, I think Jeff has a question. Oh, Jeff, you're muted.
Yeah, you're muted.
Sorry, just a quick observation, and that is when you try to extend the Fibonacci word, the one-sided Fibonacci word to two-sided, you can use either the formula for Sturmian words, or you can use
reverse.
Well, let me finish. Or you can use extended Fibonacci representation to what's called nega Fibonacci representation, which is discussed in Knuth's book, for example. And when you do this, these two different ways, you get indistinguishable asymptotic pair.
Oh, nice.
Yeah.
So that's on Z, you say?
On Z, yeah.
And you would get what kind of, how big would be the difference set in that example?
I think it's the same one that you gave, basically. So.
Oh, in that case, it would be also a Sturmian configuration.
Yeah.
Okay.
Does anyone have anything else? If not, thanks again to Sebastián.
Thank you.
Yeah, you're welcome. So we have our next talk will be on December 5th, and we'll have Josef Rukavica, who'll talk about palindromic factorizations. So thanks everyone. I'll see you all in a couple of weeks.
Thank you very much for the invitation.
Oh, you're very welcome. Thanks a lot. Bye everyone.